Hello all. Yesterday I uploaded a Unit 2 past paper from May 2025, skipping this test from January 2025, which is a Unit 4 test that I was actually planning to upload because, as I said in the video, there was a viewer who was interested in Unit 2 past papers. So I made an exception and uploaded for their sake, though I want to avoid that because, in the end, everybody will have a billion requests and it's just me. I mean, I cannot keep uploading every day, for example. I mean, it's exhausting. And this is still not a full-time thing. So the usual things I always say before we start working on a paper: you have 1 hour and 45 minutes during the real test. So that's 105 minutes, right, for 90 marks are the total marks in Unit 4 and Unit 5, I think, papers. So you should budget your time so that you spend about a minute per mark. So if a question awards 10 marks, it should take about 10 minutes. If it takes 12, it's fine, but try to stay on time so that you can score maximum points. Second thing, read the question thoroughly, make sure you understand what they're asking you to do. Okay, half the answer is in the question, as I always say. Third, this is more applicable to section B. I'm gonna go find a random question in section B. Okay, so usually section B questions have a part A, part B, part C, part 1 of part B, etc. So sometimes part A might be incomprehensible, but if you skip it and read part B might actually guide you in what the answer in part A is, and similarly for parts C, D, whatever. Okay, I hope this makes sense. The other thing is to always start. This is the fourth thing, I think. Okay, so always start with the questions that you know how to deal with first, and skip those that you don't know how to deal with. Okay, and this is important because you might get stubborn and feel like, okay, I'm gonna push through this problem, and then you might waste half an hour on a problem that you didn't know how to solve anyway, and waste those 30 minutes that you can invest in getting marks from the rest of the paper. Okay, so leave it alone. If you don't know how to deal with a question, leave it alone. Solve the rest of the questions that you know how to deal with, get your marks, and return to the problem that you didn't know how to deal with at the very end. So you have time, and maybe that way you will build momentum and confidence, and maybe you will actually figure it out that way. Okay, so don't lose momentum and confidence in problems that you don't know how to deal with immediately. Okay, I hope this makes sense. I do believe in psychology a lot. I mean, your emotional state dictates how you're going to perform in a test. So if you freaked out because of a problem, that's bad news. Okay, and the final thing, which is the fifth probably, is related to questions that you don't know how to deal with. Okay, so if you read a question and maybe it's related to, I don't know, let's pick a topic. It's related to electricity. Okay, wait, this is Unit 4, so let's skip this. So let's say it's related to centripetal force. Okay, so if you come to the back of the paper, you will see that related to circular motion are these questions, these formulas over here. Okay, so just by inspecting them, you might get inspiration about what you need to do with a question. And this is where dimensional analysis comes to the game as well. So dimensional analysis is when you're given two quantities, and if you multiply them, you happen to get a quantity that is a length, for example. Okay, so that might guide you in what the answer is. So this is how physicists solve problems. Not always, but a lot of the times. That's one of the techniques. All right, so this is all I had to say, I think, up front. So let's dive into the questions. I don't know if this kind of information that I put out in the beginning helps anyone, but let me know in the comments. So section A is multiple choice questions. So another thing about multiple choice questions, sorry, I'm not done yet, is sometimes you might arrive at the correct answer just by eliminating the wrong answers. Okay, so that's another clue for you, or technique, exam technique. So question 1, two sources produce waves with a phase difference of 40 degrees. Which of the following gives the angle of 40 degrees in radians? Okay, so the way to do this is that you have 40 degrees, and then you have to multiply by a ratio that's going to make the degrees in the numerator go away. So you immediately know that you need to divide with something that has units of degrees. So 180 is a good start. And what is 180 degrees? It's pi radians, right? So what I mean is that the degrees sort of cancel that way, okay? If we read the answers, there is nothing like that. And then immediately with dimensional analysis, you can see that B and D are wrong because we are dividing with pi. So that doesn't make any sense, okay? So you have to multiply by pi. So C is also wrong because 360 degrees corresponds to 2 pi. So A is the correct answer actually in this case, okay? Why? Because, okay, I used pi that corresponds to 180 degrees, but I can as well multiply with 2 pi, both the numerator and the denominator, and we get an equivalent expression, which is A. I hope I make sense. Moving on. 2. The standard quark lepton model includes particles called mesons. Which of the following is a meson? Okay, a photon is not a meson, it's a mediator. Okay, a pion is a meson because pions consists of a quark and an anti-quark pair. Okay, the positron is a lepton and the proton is a baryon consisting of 3 quarks. So that's wrong. Again, this is an example of a question in which if you know your physics, you immediately see that photon, positron, and proton are wrong. So you arrive at the correct answer. Okay. 3. By the way, I used to believe that there was a screeching problem with the microphone. I tested 3 different microphones that I now have, and it wasn't the microphone. There was a glass on top of my desk, okay, and when my hand was resting there, it was creating a screeching noise that the microphones picked, okay. So if anything, the microphones work perfectly actually, okay. So I removed the glass, so hopefully the screeching noise is gone. So anyway, 3. Two identical charged particles were placed in a vacuum 0.02 meters apart. The charge on each particle was 8 times 10 to the negative 6 coulombs. Which of the following gives the magnitude of the force? Okay, so we have a plus Q and another plus Q separated by 0.02 meters. Okay, Coulomb's law tells us that this is equal to K times Q squared over R squared. Okay, what is K? Is 8.99 times 10 to the 9. And the units are newtons times meters squared over coulombs squared. Okay, we don't need that right now. Okay, and then we need this charge to be squared. So options A and D are immediately wrong. Okay, and then we need the distance between the two charges to be squared. So this only happens in option B. And C is also wrong. So another example. So 3 on 3 so far. I mean, 3 multiple choice questions that you can solve just by eliminating what's obviously wrong. Okay. 4. The positron is the antiparticle of the electron. Which row of the table gives a similarity and a difference between a positron and an electron? Okay, so the similarity before we even read the table is that they have the same mass, opposite charge, opposite lepton number, etc. So options A and B are wrong because they don't have the same lepton number. And we are left with C and D. C says that the difference is a different baryon number. Okay, the baryon number for all leptons is 0. So C is also wrong. So D is correct because the electron has a lepton number of +1. Don't get confused. Okay, and the positron has a lepton number of -1. Okay. I mean, don't get confused, because you might assume negative charge means negative lepton number. No, positive lepton number for the electron. Okay. 5. In alpha particle scattering experiments, alpha particles were directed at a very thin gold foil. That's a typo, I guess. So some alpha particles were deflected through angles up to 180 degrees. Okay, which of the following could explain this observation? A, strong electrostatic forces act on the alpha particles. That's plausible. Okay, sounds promising. B, the atom is mainly empty space, but that wouldn't explain why we have large deflections. C, the charge is evenly distributed in the atom. It's not, so no. D, the gold foil was very thin. Doesn't matter here. So A is the correct answer. 6. Two coils, P and Q, are close to each other, and alternating supply is connected across coil P as shown. The number of turns on coil Q and the separation of coil P and Q can be changed. Which row of the table gives the arrangement that produces the largest EMF in coil Q? Okay, so first of all, the potential difference at P over the potential difference at Q are equal to the number of turns in P and the number of turns in Q. Okay, so but we are interested in VQ. So VQ will be NQ over NP times VP. Okay, so we need the largest EMF. Okay, so we need more turns, because you see that if we increase the number of turns in Q, we get a larger EMF in coil Q. So it's either C or D. And then the separation of P and Q, do they have to be close together or further apart? Close together is the correct answer, right? Because if they are further apart, the magnetic field will not be felt very well by coil Q, okay? Because there is a magnetic field here in coil P. So if you take coil Q further away, okay, the effect of that field will be not as strong, okay? So C is the correct answer. Okay, 7. In pair production, a high-energy photon creates a particle-antiparticle pair. In one interaction, a photon produces an electron and a positron. Which of the following gives the photon energy in joules? Okay, so the energy of the photon is going to be 2 times the mass of one electron, since do they specify? Now I'm confused. Wait, they don't specify what kind of particle it is. So yeah, 2 times the mass times c squared. Okay, so we need to see c squared in here, and we see it in all the equations here. Okay, so we cannot eliminate any just by the speed of light squared. Then the other thing that we need over there is a factor of 2. So only option C and D makes sense. Okay. So, wait, they do mention that it's an electron and a positron pair. Okay, so then it's D. Okay, sorry for confusing you. Because I was now internally debating whether it's C or D, because both are plausible, but since they specify this is an electron-positron pair, it's D, okay? Because this is the mass of the electron. C would have been plausible if they told us that we have a proton-antiproton pair, okay? Because that's the mass of a proton. Okay, so D is the correct answer. Yeah, moving on. 8. The diagram shows a particle track in a bubble chamber. Which of the following is a valid conclusion from this track? Okay, so since it bends, it's a charged particle, right? Do they specify this? No, okay. So A, it says the particle is negatively charged. We cannot tell because we don't know the direction of the field. B, the particle is moving from X to Y. Again, we don't know because we don't know the charge of the particle. C, the speed of the particle is increasing. It doesn't appear so because that's a circle, okay? That's the arc of a circle, so that's wrong. If the speed increases, then we will see something like a spiral with increasing radius, so C is not correct. And then D, the particle experiences a centripetal force. That's the correct answer because it moves in a circle, okay? So it bends because it has some charge and it's inside the magnetic field. Okay. 9. The graph shows how electric field strength varies with distance from a charged conducting sphere. So we have the electric field versus distance. Which of the following gives the electric potential at a distance of 0.5 meters from the sphere? Okay, so this gave me some trouble because I didn't know how to explain it. Okay, so first of all, we know that the electric field is the first derivative of the potential. Okay, so the area under this curve gives something that has dimensions of potential. Okay, so that's the first thing. So how can we find the potential at 0.5 meters though? Okay, so let's solve this. So dV is minus E times dr. Okay, so if we integrate dV from wherever the potential is zeroed to some distance v, so let's make this a dummy variable, then we need the integral from where the potential, from where the field is zero, and the field is zero at infinity, okay, up to the distance 0.5, okay, and we have to integrate E times dr, okay. So let me come to a clean page and explain it a little bit more. So the claim again is that since dV is minus E times dr, okay, we can integrate this from some point where the potential is zero up to the point where we are interested to find the potential, and the potential there is going to be V. Okay, therefore we have to integrate minus E times dr from infinity where the field is zero, okay, up to the point where we want to calculate the potential, okay, so that point is 0.5, okay. And recall that we can reverse the order of integration by flipping the sign, so that's equal to plus the integral from 0.5 to infinity of E times dr. But this happens to be, I mean, if we plot E versus R, okay, and this is the point 0.5, this integral is the area under the curve, okay. I hope this makes sense. Again, the key here is to realize or to think that you need to integrate from somewhere where the potential is zero, and the potential is zero at infinity, okay? So let's check the answers. I hope this makes sense. A, the area under the graph from 0 to 0.5, that's wrong, okay? B, the area under the graph from 0.5 meters to infinity, that's the correct answer, okay? And then C, the gradient of the tangent to the graph at 0.5, that's wrong because the tangent here is, I don't remember the gradient of the electric field having any meaning, at least not off the top of my head, so let's skip that. And definitely this is not something you will need at the A levels. D, the value of E at 0.5 meters divided by 0.5 meters. I don't even know what they mean by that, so D is wrong. So B is the correct answer, okay? Okay, question 10. A charged capacitor C1 stores energy W1. A charged capacitor C2 stores energy W2. Okay, C1 has half the capacitance of C2, and C1 is charged to half the potential difference of C2. Which of the following shows the ratio W1 over W2? Okay, so let's start with W1, which is 1/2 C1 V1 squared, right? And they tell us that C1 is half the capacitance of C2, and C1 is charged to half the potential difference of V2. So let's plug that in. So V2 over 2 squared, right? So this is V1. Okay, let's work this out. So we have 1/2 C2 over 2 times V2 squared over 4, which is 1 over 8 times 1 over 2 C2 V2 squared, right? But what is this? This is W2, right? So we immediately infer that W1 over W2 is 1/8, okay, which is option A. Okay, this is an example where you actually have to do the work. So both 10 and 9 were examples in which you have to do the math pretty much. So the technique of eliminating the wrong answers doesn't work here, but it's fine, okay? Let's move on to section B now and question 11. So question 11, a nuclear reaction that occurs in the sun is shown. Two protons turn into a proton and neutron, a positron, and an electron neutrino. Two protons react to form a proton and neutron, positron, and an electron neutrino. Okay. I was reading the reaction without reading what was stated there, so I stated the same thing twice. Anyway, energy and momentum must be conserved in this reaction. Explain how 3 other conservation laws apply to this reaction. First of all, for the record, there is something called the PP chain, which is a series of nuclear reactions that have, take place in the sun or stars like the sun. So stars that have a mass of less than about 1 times the mass of the sun, okay? So it's part of the hydrogen burning cycles that occur in stars. The other one is the CNO, I think. Look it up because I'm a little bit rusty with these things. The CNO cycle happens in heavier stars, I think. So that's carbon burning and stuff like that. Anyhow, so the other conservation laws are, so the charge must be conserved, okay? What's the charge of 2 protons? Plus 2. And what's the charge on the right-hand side of the reaction? So we have a proton plus an electron, plus a positron, so 2, so that's conserved. The other thing is the baryon number. The baryon number before is plus 2 because of 2 protons, and the baryon number after is also 2 because you have a proton and a neutron, okay? And then the last number is the lepton number, and you need to be careful with this one. So 0 lepton number before, because protons are baryons, they don't have a lepton number. And after, we have a positron that has a negative lepton number and an electron neutrino that has a positive lepton number. So that's 0 again. So that's conserved as well. So these 3 laws must be conserved. All right, and look up the PP chain for those of you who are curious about nuclear astrophysics. This is the field, guys. Okay. The diagram shows a Van de Graaff generator. This is a device that produces a large potential difference by charging a conducting sphere. And whenever I encounter a Van de Graaff generator, I will always say that President Trump's uncle was the PhD student of Van de Graaff himself at MIT back in the 30s, I believe. I mean, the 1930s, because we are approaching the 2030s fast. So that was about 100 years ago. I think he was the paternal uncle, something like that, from his father's side. Okay, so he was the brother of his father, I believe. So anyway, so if President Trump is watching, please sponsor the channel. Give me a golden visa, I don't know, something like that, help the situation. So, anyway, again, I don't want this channel to creep into politics. I just want to keep it light and keep on the scientific side of things. And President Trump's uncle was a good scientist back in the day at MIT. If anybody's interested, I can dive deeper into his story and tell you more. So anyway, moving on. The conducting sphere of a Van de Graaff generator has a radius of 22.5 centimeters. the electric potential produced at the surface of the conducting sphere is 1.75 times 10 to the 4 volts. Show that the charge on the sphere is about 4.4 times 10 to the minus 7 coulombs. Okay, so the potential, I was going to say the voltage, which is not wrong, but okay. So the potential at the surface of the sphere is K Q over R. So that's R, K. So we are looking to find the charge on the sphere. Okay. So Q is what we have to solve for. Q is V times R over K. And we just have to plug in numbers. So 1.75 times 10 to the 4 volts. And I'm going to write volts as joules per coulomb. Okay, so that's a volt. You have to get comfortable working with these units, guys. Okay, times 0, where was it? 0.225 meters. And then we have to divide by K. K is 8.99 times 10 to the 9. And that's newtons times meters squared over coulombs squared. Okay, so let me erase this because it's confusing. Okay, so let's see. This coulomb cancels, the meters cancel, and then newtons times meters make joules. So joules cancel, so we are left with coulombs, and I will need extra space to write the final result for Q. So Q is 4.38 times 10 to the negative 7 coulombs, so about 4.4 times 10 to the negative 7 coulombs. All right. B. Neon bulbs. Light when placed in a region of strong electric fields. A neon bulb is moved towards the charge sphere of the Van de Graaff generator. The neon bulb lights when the distance between the neon bulb and the center of the charge sphere is 32.5 centimeters, so 10 centimeters away. So when you put the neon lamp here, okay, so at a distance of about 10 centimeters. Okay. Determine the electric field strength at this position of the neon bulb. Okay, so E is going to be KQ over R squared. Okay, and we are going to take the field from the center of the sphere. So we're going to use this distance as the distance where we are calculating the electric field. Okay, so the 0.325 meters. Okay, so 8.99 times 10 to the 9, the units are newtons, meter squared over coulombs squared, times 4.38 times 10 to the negative 7, and that's coulombs, right? So coulombs here cancel. And then we have to divide with the distance squared, so 0.325 squared, and that's meters squared. Okay, so the answer is 37,279.2 newtons per coulomb, and newtons per coulomb are equivalent to volts per meter. Okay, and because this is a teaching channel, you might be wondering why does the neon bulb lights up near the presence of an electric field? I mean, it is not connected to a voltage or anything, so you just take the bulb, put it next to the Van de Graaff, and it lights up. Why? Okay, you don't need to specify this in the exam. It doesn't have to do with the exam. It's just for those of you who are curious. So the field is strong enough, okay, to knock electrons in the neon atoms, in the neon gas atoms, out of their orbitals. Okay, and so when they go back to their ground state, when they go back to the ground state, okay, light is emitted. Okay, so this can actually be an A-level question in some other test, because it makes sense. Like someone might ask you why. So the reason is that you have neon. Neon is neon 10, right? I think it has 10 protons. Doesn't matter. So here are the electrons. They sit there. Okay, and then we bring an electric field which is strong enough to make the electron jump to a higher orbital. Okay, so as it de-excites, it emits light. Okay, so that's the explanation why the light bulb lights up. Okay, again, this is not something you need to know. Okay, no, this is not something you need to answer in this test, but it's good to know. Okay, so yeah, let's move on to question 13. Okay, question 13. A power cable is supported by two pylons as shown. The length of the cable is 90 meters. The current in the cable is 700 amps. Near the pylons, the Earth's magnetic field has a magnetic flux density of 48 microteslas at an angle of 20 degrees to the vertical. Determine the force on the cable due to the Earth's magnetic field. Okay, so you hear 20 degrees angle, so your first instinct should be to resolve the magnetic field flux density vector. Okay, that was a mouthful. Okay, so in other words, you can analyze this into a component that is horizontal and parallel to the cable. Okay, and a component that is perpendicular to the cable, like that. Okay, so that angle is 20 degrees. So this component is B sine 20 degrees, and the other one is B cosine 20 degrees. The rule I use to remember it is that this component, the one I'm drawing right now, touches the angle 20 degrees. So that's the cosine component, while the other one, the sine component, doesn't touch the angle, if that makes any sense. And of course, you can work it out with math. Okay, that's the first thing. The second thing is to realize that, okay, the current goes in this, do they specify? Doesn't matter. So the current might be going in this direction or that direction. I think it doesn't really matter. So the important thing that does matter is that this component, the B sine 20 degrees, is parallel to the current. Therefore, no force is exerted. Okay, so only the component that is perpendicular to the current experiences a force. So let's write that down. B sine 20 degrees is parallel. That symbol means parallel to current. So no force. Okay, so F is F bill, but B is B cosine 20 degrees. Okay, times the length times the current. So we have 48 times 10 to the negative 6 Teslas times, I'm gonna run out of space. Let me erase this. Okay, and come down here. So 48 times 10 to the negative 6 Teslas times the cosine of 20, which is 0.94, times the length, which is 90, right, meters, times the current, which is 700 amps. That's a really strong current. Okay, so the answer ends up being 2.84 newtons. How do we know that these units, Teslas times meters times amps, work out to newtons? So we're gonna use something of a circular argument, really. So F is B times I times L, right? So newtons is equal to Teslas times amps times meters. Okay, so it's a circular argument, but it works, I think, in this case. So yeah. Okay, so that's the answer. So that's a very small force, but not insignificant. So it kind of bends the cables a little bit. I mean, it exerts a force, a very small. That's a much smaller force, of course, than their weight. Okay, I mean, if you think about those really long cables out there. So, all right. Hope this is clear. Let's move on to the next question. Okay, question 14. A cathode ray tube can be used to demonstrate the properties of electrons. In the cathode ray tube, a beam of electrons is produced using the arrangement shown. So I hope this is not confusing. It is a little bit confusing the way they show it, but this AC supply warms up that filament that emits electrons via thermionic emission, and this DC current, direct current, okay, DC voltage accelerates those electrons towards this vacuum there. And in case you're wondering why this is important, cathode ray tubes were the standard in televisions up to and including the 2000s, maybe. When was it the 2000s? I don't remember clearly, but I do remember cathode ray tubes because I'm 1,000 years old, as you guys have probably figured out. So back in the day, you had cathode ray tubes that shoot electrons towards the screen, and that's how you watched television. Was it dangerous? I think it was a little bit, okay? I mean, you shouldn't, like when I was a kid, my parents would scream at me if I went really close to the television, and there was heat, okay, because of the electrons hitting the screen. Okay, it was behind the screen, but you get the idea. All right. Explain why electrons are released when there is a current in the filament. That's the first question. So current heats up the filament, okay, as it runs through it. We have to, yeah, let's leave it there. So current heats up the filament, okay. So free electrons in the filament gain energy, okay. So some electrons gain enough energy to escape, and this is called the thermionic emission of electrons, okay. It doesn't happen with ions, okay, as far as I know. And thermionic, I mean, if you speak Greek, thermos means warm, okay. So emission via heat, okay. B, in the cathode ray tube, the electrons in the beam had a de Broglie, Prince de Broglie, wavelength of 2.65 times 10 to the negative 11 meters. I always call him Prince de Broglie because he came from an old aristocratic French family, okay. Remember the French Revolution, the French abolished the monarchy, but I think some people maintained some of their status. One of them was de Broglie, I think. So calculate the potential difference V required to accelerate these electrons between the electrodes. Okay, so we need to work in steps. So lambda is h over p, right? But we don't know what p is. Let me think. What are they asking to calculate the potential difference? Okay, so lambda is h over p. Now the kinetic energy of this electron is p squared over 2m. What provided that kinetic energy? The electric potential. So V times E, okay, is p squared over 2m, okay, because the energy of a particle inside an electric potential is Q times V, right? So this is what I'm using here, where we replace Q with E, okay, and V is the potential. All right, now let's also use the fact that P is h over lambda and plug everything in. So we will find that V is h squared over lambda squared, right, which is p squared, and then we have to divide by 1 over 2m times E, where m is the mass of the electron. Okay, so I hope this makes sense. I'm gonna move to a clean page. So V is Again, h squared, I don't know why I'm using purple, I liked it, 2me times lambda squared. Okay, so we have 6.63 times 10 to the negative 34 squared. The units are joules squared, seconds squared, and then in the denominator we have 2 times the mass of the electron, 9.1, 9.11 times 10 to the negative 31, that's kilograms, times, I'm gonna run out of space again, so let's move this down here. Okay, here, that looks good. And actually, let's erase the units and put them further out here. So joules squared, seconds squared, what was the other one? Kilograms, okay. And then we have to multiply with the charge, 1.6 times 10 to the negative 19 coulombs. And then we also have lambda squared, okay. So lambda is 2.65 times 10 to the negative 11 squared, and then we need meters squared. So we're gonna work out the units eventually. Let me first give you the number that comes out of all this craziness here, okay? So the number is 2147.2. Okay, so let's work this out. So let's take these units, let's work the units out. So first of all, we have joules squared over Coulomb. We're gonna pick one of those joules and do it like this, joules over coulombs, okay? And then we have another joule that I will write as kilograms meter squared, second squared. By the way, this is just me being pedantic. If you write there volts, that's fine, okay? That's the answer. I just want you to see how volts come about, okay? So again, let's move this further down. I'm sorry about that. Okay, keep going. So we started with this joule squared and coulombs. So I analyzed it as joules over coulombs times kilograms meter squared over second squared. That's a joule, okay? And then we are still left with seconds squared in the numerator, and then meters squared in the denominator, and then kilograms in the denominator. So second square go away, meter square go away, kilograms go away, and we are left with joules over coulombs, which are volts, okay? So this is how the volts come about in this answer. Okay, so this took a little bit longer than I anticipated, but let's keep moving to the next question. Okay, 15. A washing machine uses a rotating drum to wash clothes. The photograph shows the drum inside a washing machine. The clothes are put in the drum. The drum is a hollow metal cylinder with a series of holes through its surface. At the end of the washing process, the drum rotates at high speed. The drum of the washing machine rotates at 1400 revolutions per minute. Show that the angular velocity of the drum is about 150 radians per second. Okay, so whenever you see something like this, revolutions per minute, you should always think frequency. Okay, so let me show you. So omega, by definition, is 2 pi times the frequency. Okay, so that's 2 pi times 1400 what? Revolutions, so that's a pure number, per minute. 1 minute is 60 seconds, okay? So you have your radians from 2 pi, you have your seconds, so you get an angular velocity, right? Let's verify that. If we multiply this, we get 146.6 radians per second, which is very close to 150 radians per second, which is what they ask us. Okay, so good. 2. The diameter of the drum is 45 centimeters. Calculate the centripetal acceleration of a point on the circumference of the drum. Okay, the angular acceleration is omega squared times r. Okay, so that's omega squared times d over 2 because they give us the diameter. Okay, so we have 146.6 squared, and that's seconds to the minus 2, but okay, I'm going to write it in the end, times 0.45 over 2, so meters per second squared, okay? So that gives us 4,836.1 meters per second squared. All right. Part B. As the drum rotates at a high speed, clothes move in a vertical circle resting against the side of the drum. The dot in the diagram represents an item of clothing as it rotates with the drum. Add label arrows to each diagram to show the forces acting on the item of clothing. So in this occasion over there, we have the reaction force from the drum, let's call it N, and the weight of the clothing, M times G. In the other circumstance, we have again the reaction N and the weight M times G, pointing in the same direction. All right. 2. The drum rotates at constant speed. Explain how the forces on the item of clothing vary between the bottom and the top of the drum. So, M times G and M omega squared times R are constant since omega is constant. This is what they tell us. Okay, so let's analyze what's going on at the bottom. We have the reaction force minus M times G must be equal to M omega squared over R. So the reaction force is N is equal to M times G plus M omega squared times R. So it's very strong. Okay, how do we know that we have to subtract M times G from N? It's because we need a centripetal force pointing inwards, okay? And it's the same centripetal force we need in the other occasion, okay? Because we need the sum of all forces to point inwards to have a centripetal force. Otherwise, the object is going to fly off, right? Okay, so that's the bottom. Let's do the top. We have N plus M times G is M omega squared times R. So N is M omega squared times R minus M times G. Okay, so N bottom is larger than N top. Okay, so that's the conclusion. And another thing is, this is the necessary condition to even have circular motion. Okay, so if N becomes 0, which means that the clothing barely makes it, we will have M omega squared R. You don't need this for this paper, okay? M omega squared R is M times G, okay? So omega must be larger than or equal to G over R, the square root of that, okay, to have circular motion. All right, and we're left with part 3. Water leaves the drum through the holes as the drum rotates. Describe the path of the water as it leaves the holes. So I'm gonna draw a circle and show you. Okay, that's a nice circle. Okay, so let's say that we have water there. So it's gonna fly off at a tangent pretty much to the circle. Oops. Yeah. So it's gonna fly off like that. So water. Actually, that's the wrong color. Let's use blue. It's water, right? Sorry. So it's gonna fly off tangent to the circle. So water. If it's at that point, it's gonna fly off in that direction. Okay. So water and water, etc. So why is that? So once water leaves the hole, okay, no centripetal force acts on it, okay, so it continues in a straight line tangent to the circle. All right. Okay, question 16. In the early 20th century, Milligan carried out an experiment to determine the magnitude of E the electronic charge. Charged oil droplets were introduced into a region of electric field produced between two parallel plates. Fun fact, Robert Milligan is my academic ancestor, meaning, okay, in academia, especially in physics, I don't know why they like this, but it's fun. You sort of have an academic father who is your PhD advisor. Then you have an academic grandfather who is the advisor, the PhD advisor of your PhD advisor, and so on and so forth. So down the line of advisors, I have Milligan, and I have many other great physicists. So I'm kind of like the black sheep of this line. I'm sorry, guys. I never made it into being a faculty member, so I have PhD students on my own. Not yet, but it will take several miracles happening at once for that to happen. So yeah. Anyway, so let's move on. A potential difference was connected across the plates. Add to the diagram to show the field lines between the plates. Okay. So usually you have a plus and a minus, and you immediately instinctively do that. But that's not the trick to remember. So the trick, the trick is that the lines, the electric field lines, go from areas of high potential to low potential. Okay, so plus V is higher than 0. Okay, so the lines go from plus V to 0. They have to be equidistant. So a few lines, it's fine, but I'm gonna try to be thorough. Okay, so they have to be equally spaced, guys. Okay, it's not perfect, but something like that. All right, so part A is done. Let's move on. B. A charged oil drop entered the region of electric field between the plates. The plates were 1.5 centimeters apart. A potential difference of 85 volts was applied between the plates, and the charged oil drop was brought to rest. Deduce whether the charge on the oil drop was a whole number multiple of the electronic charge. They give you the volume of the oil drop and the density of oil. Okay, so let's go back to the diagram and show the drop. Okay, let's make it green because it's olive. Okay, so this is going to be experiencing the its weight, right? So m times g, and therefore, since it's brought to a rest, it experiences a force upwards, which means that it's actually negative. Okay, how do we know that? Because if it was positive, it would be pushed this way, so it will never come to rest in this arrangement, at least. Okay, so the Coulomb force is up, and it's negatively charged, as we just said. Now let's turn the page. So F Coulomb is going to be equal to m times g. What is the Coulomb force? Okay, now what did I do here? So let me think. So the force in general is Q times the electric field, right? And this is going to be equal to m times g, but we are not given the mass, we're given the density and the volume. So rho, the density is m over v. So the mass of the droplet is its density times the volume, right? Okay. So Q times E, which is F Coulomb, is equal to rho times V times G. Okay, now what is the charge? What is E in this arrangement? E is, oops, what am I doing? E is the voltage, I'm gonna write it like that, okay, over the distance, okay? And this is equal to rho times V times G. So let's solve for Q to see what do we find. So rho times the volume times G times D, right? Over the voltage. Okay, 920. That's the density. So let me create some space. So for the units, so kilograms over meters cubed. Okay, times the volume. What's the volume? 5 times 10 to the negative 19 cubic meters. What is G? 9.81 meters per second squared. And then D is the distance between the plates. So 0.015, and that's meters. So I'm going to put it as meter squared there. And then divided by the voltage, which is 85. Okay, 85. And then I'm going to write it as volts. Yeah, let's write volts. Okay. We find 7.96 times 10 to the negative 19. And okay, let's do some simplifications here. So we have meters cubed and meters cubed cancel. And then we have kilograms times meter squared, so over second squared. So this quantity here is the joule, okay? And then we have joules over volts, but volts are joules over coulombs. Okay, so we find that answer. And if we divide, let's use a clean page. So Q that we calculated over E is going to be 7.96 times 10 to the negative 19 coulombs over the fundamental charge, which is 1.6 times 10 to the negative 19, also coulombs. So is this an integer number? So 7.96 over 1.6, it's 4.98. Okay, so it's about 5. So it is an integer multiple of the fundamental unit. So yeah, Milligan was brilliant in thinking this out. All right, let's move on to the next question. Okay, next question is 17. So we have a simplified diagram of a cyclotron that is shown. In the cyclotron, protons gain energy. Protons are produced in the source and initially travel in the direction shown. Okay. A magnetic field is applied perpendicular to the Ds. The magnetic field direction is into the page. Okay. So B is into the page. Okay. So that's the way we denote it. So it's like looking at an arrow going into the page from behind. So you see the tail of the arrow. Okay, question A. Add to the diagram to show the path of the protons as they gain energy in the cyclotron. Okay, so the relevant equation is, so you have to show the path pretty much. So we have to apply QVB, okay. So we have to apply Fleming's left hand rule. And I remind you that the index, that you have to point the index of your left finger is important, okay? Don't use the right, the left. So your index should point into the direction of B. Then the current or charge should be your middle finger. So the direction of motion of the charge should be pointed at using your middle finger. So your thumb is then going to show the force. Okay, so in this case, we have a magnetic field going into the page. So I'm putting my left hand showing into the page. Then my middle finger points in the direction of the charge, which is to the right, as we see. So we see that our thumb points up into the page. So there is a force that points up in that direction, okay? Therefore, the protons will undergo a spiral motion in this direction, okay? So they go to the right, and then they go around, and they gain energy, and so on and so forth. So I hope this makes sense. If it's confusing, let me know in the comments. Let me redraw. Okay, so something like that, with the force F pointing up, okay? So the force is perpendicular to the speed, and the speed is tangent to that orbit or direction of motion. Okay. B, the frequency F of the alternating potential difference applied to the Ds is given by the equation BQ over 2 pi m, where m is the mass of the proton, B is the magnetic flux density, Q is the charge of the proton. calculate the time a proton spends in one of the Ds. Okay, do we have enough space? We don't. So maybe I'm going to use a clean page, okay, for this question. Actually, let's start here and see how it goes. So let's first calculate F, okay, and from there we will calculate the period. So F is BQ over 2 pi m. So 0.55, and that's Teslas, then times 1.6 times 10 to the negative 19, which is the charge of one proton in coulombs, and then over 2 pi times the mass of one proton, 1.67 times 10 to the negative 27. So we have kilograms, and this evaluates to 8.39 times 10 to the 6, and the units must be hertz. As I have done throughout this test, I'm going to show you why Teslas times coulombs over kilograms evaluate to hertz. So let's do that. So from F equals to QVB, we immediately infer that newtons are equal to coulombs, which is the charge of, which is the unit of charge, times meters per second times Teslas. Okay, so Teslas can be written as newtons times seconds over coulombs times meters. Okay, so in our example, we have units of Teslas times coulombs over kilograms, and if we plug in, we immediately see that we have newtons times seconds times coulombs over coulombs times meters times kilograms, so coulombs cancel, and we convert newtons to kilograms times meters over seconds squared, which you can find from F equals ma, okay? Then times seconds over meters and kilograms, okay, so everything cancels, and we are left with seconds to the minus 1, which is hertz, okay? So the unit here is hertz. Okay, now we're not done yet. The period is 1 over the frequency, so 1.19 times 10 to the negative 7 seconds, okay? Let me think. So the proton crosses both these in one full period, right? Okay. So the time in 1D, so the time spent in 1D is period over 2, or 0.6 times 10 to the negative 7 seconds. And this is all there is, but just for completeness, 1t, so one period, so in 1t, so in one period, in 1t, polarity between the D's flips from plus to minus and then plus again, okay? So that in every revolution, the proton always gets accelerated. I hope this makes sense. So yeah, this was a little bit longer than I intended, but I hope it's complete. We basically proved why that unit is hertz, even though during the test you can just write it down that it's hertz, hertz, okay? And since during one period it goes through a full revolution, then for half a revolution we find the time in 1D, in one of the two Ds. Okay, so let's move on to part C. Okay, C. This is a long writing problem awarding 6 marks. So, okay, the usual rule I always say applies, that you should spend about 6 minutes, though it can take you longer. But the most important thing here is that to get all 6 marks, you usually have to provide about 6 independent sentences explaining whatever it is they are asking you. So let's go read. Explain how the cyclotron increases the energy of the protons. You should refer to the alternating potential difference and the magnetic field. Okay, so this is a little bit complicated. I mean, it will take a lot of writing, I'm sorry. So the alternating potential difference creates an electric field, okay, across the gap between the D's, okay. The field, so this electric field, this E, I'm gonna write it like that, accelerates the proton every time it crosses the gap. Every time it crosses the gap. Okay, inside each D, okay, there is no electric field. Let me go fix something, okay. There was the check spelling ticked, which means that's why you saw those red underlines. So anyway, inside each D there is a no electric field, okay. So the proton's speed stays constant. Okay, the next thing is that B acts on the moving proton, okay, and provides the centripetal force needed for it to curve. The centripetal force needed for it to bend, okay, it's better to put it that way. Okay, as the proton's speed increases, okay, this circular path has a larger radius each time. Okay, the polarity, as we just said, the polarity switches every half cycle. Okay, this switching, okay, this switching is timed so that the proton has time to pass through the D. Is time so that P has time to pass through the D. Okay, let's create a clean page. Each time the proton reaches the D, gap again, the far side has become oppositely charged. Okay, so this means that the P is always accelerated in the same way at every crossing. Okay, so the protons speed up and energy increases. Okay, I think I mean this one overshooted. Okay, next time I will provide a shorter answer. I don't know what got into me and I wrote all these things, but okay, this is a very complete answer, but I'm pretty sure you can write it down. You can summarize this and make it shorter, okay? Because it's too much for a test like this because it's gonna take a lot of time to write up. All right, anyway, let's move on. Okay, question 18. The diagram shows a key card and a card reader used to unlock a door. To unlock the door, the key card is moved downwards through the card reader. Okay, the key card contains a magnetic strip consisting of many tiny bar magnets arranged side by side. The orientation of the magnetic poles of the bar magnets stores a code to unlock the door. In the card reader, there is a coil connected to a voltage sensor as shown below. Okay. A. Explain how the voltage sensor detects the orientation of the magnetic poles. Okay, so this is another writing problem that awards 4 marks. So you have to provide about 4 sentences. Okay, that's the rule. So as the card moves, okay, each magnet on the strip, okay, passes close to the coil. Okay, this changes the magnetic flux passing through the coil. Okay, a changing flux induces an EMF in the coil, and we can see this, I mean, from the diagram. There's a coil there, so if we change the magnetic flux by alternating these magnets and moving down, the magnetic flux there in the coil changes, so there will be an EMF and a current generated in that circuit. Okay, so let me use a clean page. Whether the EMF will be positive or negative depends on whether a north or south pole, is passing at the moment. Okay, reading the sign of the voltage tells you the orientation of the magnet. Okay, another long answer, I'm sorry, but I think it's complete. So let's move on. Part B. The card reader can determine the orientation of a magnetic pole if the reading on the voltage sensor is greater than 1.5 times 10 to the minus 6 volts. The key card is moved down a distance of 9 centimeters through the card reader in a time of 0.032 seconds. Deduce whether the card reader can determine the orientation of the magnetic pole. They give you the number of turns on coil, the magnetic flux density, and the width of each magnet. Okay, let's start from the definition of EMF, which is minus the change in magnetic flux linkage over time. Okay, and we will drop the minus sign because we are interested in the magnitude here. Okay, so let's keep writing. We will drop it at the end. So okay, so this is equal to the change in N times the magnetic flux is equal to the magnetic flux density times the area over delta T. Let's keep going. N and B are constants, so they come out of that expression. Okay, and we are left with the area. Okay, so the area is equal to the width times the distance traveled over time. Okay, the width is also constant, and we are left with delta x over delta t, which is nothing but the velocity, right? So that's minus nb width times velocity. So the absolute value of the electromotive force is equal to the number of turns times the magnetic flux density times the width of the card times the speed. Okay, and the speed can be calculated with by using the distance over time, right? All right, so now let's plug in numbers after all these calculations. So I'm coming over here. So we have, let's see, 25 times 2.4 times 10 to the negative 5 times 0.98 times 10 to the negative 3 times 9 times 10 to the negative 2 over 0.032, and the units are Teslas meters squared over seconds, which is, so this is equal to 1.65 times 10 to the negative 6. That's good news, okay? Because remember, they say that it has to be larger than that, okay? But does this evaluate to volts? Let's see. Remember that earlier we said that a Tesla, where was it? Over here. So that's the unit. This is what the Tesla means, okay? So let's go use that. I'm sorry if I make you dizzy. So the Tesla is, 1 Tesla is 1 Newton times seconds over coulombs times meters, okay, and then we have meters squared over seconds, so seconds go away, that meter gets cancelled, so we have newtons times meters, which is equal to a joule. Joules over coulombs are volts, okay, so 1.65 times 10 to the negative 6 volts, which is larger than 1.5 times 10 to the negative 6 volts. So this works. Okay, this was question 18, right? So we are ready to move on to question 19. Okay, 19, the photograph shows a theme park attraction. Small electric cars are driven on a horizontal surface. The cars sometimes collide. Question A, there is a thick rubber strip around the base of each car. Two cars collide and come to rest. Explain why the rubber strip reduces the likelihood of injury to the drivers. You should refer to change in momentum. Okay, so the rubber band, the rubber strip, I'm sorry, not band, squashes and deforms. So let's say deforms during collision. Okay, double S. Okay, this stretches out. Oops, what did I write there? This stretches, yes, out the collision time. Okay, the change in momentum, okay, of the car is fixed either way, since the cars end up at the same speeds. So but F times delta T is delta P. So F is proportional to 1 over delta T. So if delta T increases, F decreases. Okay. So this, okay, smaller force on the driver reduces injuries. Okay, so that's a complete answer, I think. So let's move on to the second part of this question, B. In another collision, car A collides with car B. Car A is initially traveling at 2.19 meters per second in a straight line. Car B is stationary. After the collision, car A moves with a velocity of 1.21 meters per second at an angle of 48 degrees to its original direction. Car B moves with a velocity v at an angle 33 degrees to the original direction of car A, as shown. Deduce whether the collision is elastic or inelastic. Okay, so basically you have to find the speeds now, okay, because the speed of car B is unknown. So let's divide the situation into before and after. So before and after. Okay, so we have car A traveling with 2.19 meters per second to the right, so that's A. So B is stationary, and then after we have A traveling at the speed of 1.21 meters per second at an angle of 48 degrees, and B travels with a speed which is unknown at the direction of 33 degrees. Okay, let's create a clean page. So we need to find the speed of B. The best way is to use conservation of momentum in the y direction. We have conservation of momentum in the x direction as well, but that's not very useful. So in the y direction, we have ma times va times the sine of 48 degrees is equal to b times vb times sine of 33 degrees. Okay, which means that vb is MAVA sine of 48 degrees over MB sine of 33 degrees. So this is equal to 390 times 1.21 times 0.74 over 360 times 0.54, which is equal to 1.8 meters per second. Okay, so let's find the kinetic energy before. That's just 1/2 m ua squared, the initial velocity. So 1/2 390 times 2.19 squared, which is equal to 935.24 joules. Okay, and the kinetic energy after is 1/2 m VA squared plus 1/2 MB, so that's MA, I'm sorry, MB VB squared. So this is 1/2 390 times 1.21 squared plus 1/2 360 times 1.8 squared, and this evaluates to 868.7 joules, so not elastic. Okay, so this was problem 19, and we are moving on to the last problem. This was a long test, guys. I wouldn't say difficult, but long. Okay, so okay, long usually means difficult, you get tired, you know, that kind of thing. So let's move on. Okay, 20, a student connected the circuit shown to investigate the charging and discharging of a capacitor. She connected the switch to position X to charge the capacitor. Explain how the current in the circuit varies when the switch is connected to position X. You do not need to do any calculations. So another writing problem. I mean, there were too many in this test, I feel. So at the beginning, C, the capacitor, has no charge. Okay, so the full potential difference, so the full PD is across R, and I is maximum, the current is maximum. Okay, as C charges, the PD across the capacitor rises. Okay, since the PD is fixed, the supply potential difference, okay, the battery, I mean, the PD across R must fall. Okay, current is proportional to the potential difference. So let's create a clean page. So current is proportional to the potential difference across the resistor, right? Across R. So current falls too, because current is voltage over resistance, right? Once C is fully charged, okay, all the supply PD is across it, okay, and none is left to R. None is left to R, the resistor, so current is 0. Okay, another long problem. So, okay, we're done with part 1. Part 2, sketch a graph to show the variation of current in the circuit as the capacitor is charged. Include the maximum value of current in the circuit. So the maximum current is going to be the voltage 8 over the resistor, 125,000, okay, so volts per ohm. So that's 6.4 times 10 to the negative 5 amps. So let's put there, that's 6.4 times 10 to the negative 5 amps. And we will have a decay curve like this. Okay, so that's current, that's time. Part B, to discharge the capacitor, the student connected the switch to position Y. Okay, so there. So we see that there is only a resistor and a capacitor in that setting. Okay, show that the time constant of the circuit is about 60 seconds. Okay, so the K constant is RC, so 125,000 times 470 times 10 to the negative 6, which is 58.75 ohms times farad, which evaluates to about 60 seconds. Shall I show you why ohms times farads is seconds? No, let's save time. Okay, we've done this enough times, so no. 2. The student connected the switch to position Y for a time of 3 minutes. Determine using the time constant of the circuit the percentage of the original potential difference remaining across the capacitor. Okay, so V is V naught e to the minus t over the time constant. So V over V naught is e to the minus t over the time constant, which is e to the minus 180 over 58.75, which is equal to 0.0467 or about 4.67%. Okay, keep moving. Part C. After the capacitor was fully discharged, the student connected the switch back to position X to recharge the capacitor. The student used the voltage sensors to measure the potential difference VC across the capacitor VC and the potential difference VR across the resistor. Both sensors were attached to a data logger. The output from the data logger is shown below. Determine the value of the PD and the value of the time where the two lines intersect. Okay, so the trick here is that where they intersect, VR is equal to VC, right? So VC plus VR is 8 volts, and VC is equal to VR. Okay, so 2 VR is 8 volts, so VR is 4 volts, and we can use the exponential function to find the time. So 4 volts is equal to 8 volts, the initial, e to the minus t over tau, so volts cancel. So we have e to the t over tau is 2, so t is ln of 2 times tau, which is 40.72 seconds. Okay, using just that trick, okay, the voltage has to add up to 8 volts pretty much. Okay, so if they are equal, they get each they get 4 volts each. Okay, moving on to part D. The student connected a second identical capacitor in series with the first capacitor. She connected the switch to position X to charge both capacitors. Explain how the magnitude of charge stored on each capacitor compares with the charge that was stored on the single capacitor. You do not need to do any further calculations. So capacitors in series store the same charge, okay, and two identical ones in series halve something's wrong. Okay, so halve the total C. So 1 over C plus 1 over C is 1 over C total, which means that C total is now C over 2. Okay, so same voltage, same V, half the capacitance. Okay, so now each capacitor stores half the original charge. Okay, this was a really long test. I don't know why it felt long. Okay, so So another video, guys. Okay, I keep trying to keep up with the channel. As you know, there are plans on uploading material unrelated to A-level physics, but that's a different channel. I mean, it's within the same channel, I mean, but it's a different series of videos that you are welcome to watch. But I will keep uploading A-level papers as well. I receive lots of positive comments in these videos, but the channel is still not growing as much as I would like. So it's getting really hard to keep going. So please like, subscribe, and help me to grow this channel and hopefully make a living out of it, because I kind of need it. So see you in the next video. Bye.